My name is Caden Freeman, and we are presenting the water tower design for Cotito Uganda proposition. This presentation will be presented by me, Caden Freeman, and Landon Scott, and Frank Martinez. Enjoy. So the first thing that we wanted to talk about was why did we pick Cotito? So one of the main reasons we picked Cotito is because of the water crisis that is going on there. It's really important to recognize that with a small population, around 20,000 people in like the metro, so-called metro area of Cotito, there's like a Cotito district, which is a much bigger area, and then there's the town of Cotito, if you ever look it up. And this like population of about 20,000 people, they face like persistent challenges of not only having access to water, but having access to clean water. Um, and to solve this, they have to walk many miles every single day, especially the women and children, to get this water. And this takes time away from economic activity, from education, and growth for the community. So we want to come up with a solution for this. And a water tower can do that by giving them extra time to have clean access to water and have the right for growing their community. So we want to partner with Wells of Life, Water.org, and Uganda Water Projects to help support the community in this area that they may be lacking. Okay, so the next question we have to ask ourselves is where in the town of Cotito are we going to place this water tower? And the place we have selected was based on topographical data where the most northern part of the town had a higher elevation, and furthermore, it was placed near the Cotito River, which would be a good source during the wet seasons where it runs more strongly. Um, Another aspect to that is that allows us to have a gravity-fed water distribution system, which helps make less maintenance and need for pumps and costs and lowest costs and everything for a town that doesn't need extra costs and things. A water tower to take care of. They want the water tower to serve them and not something to be constantly needed to be maintained by people who may or may not have the expertise or time to be able to do this. Furthermore, another way to solve this issue of being further outside the power grid is that we can use solar powered pumps if pumps are needed. These are both sustainable and easy to maintain, and this can help get the water actually into the water tower and ready to serve the community. Okay, so now we're getting to the vision and mission of this project. So our goal is to serve about 20,000 people, and each person needs about half a gallon per day. So what this maps out to, if we want to have 2 weeks worth of water supply, is about 140,000 gallons of tank capacity. So why do we want to make it last for 2 weeks? Well, this region tends to have a high amount of drought, so we wanted to have be more of a medium-term solution rather than some sort of short-term where only 1 or 2 days it can support the population, then people have to go fetch water again, which would be a waste of time that they need. So that's why we decided to do more of a medium-term solution of about 2 weeks. Um, so there's a study by WHO and UNICEF that says that every $1 invested in clean water returns at least $4 in economic benefits. So overall, despite the amount of investment that might be needed for the water tower, they're going to have it paid back by the amount of time that they save and the time they can invest in other things like education and other economic activity. So if you do the math and you say that this saves them about 15% of productivity, that can translate to over $250,000 in GDP growth in that area. So the social investment is just all paid back for itself. So it's not only just like some sort of charity project. Like this makes sense to serve these people and give them clean water and dignity for the future, the education, the health, the economic transformation in the town. So that is our goal, our vision, our mission. Okay, so what are some other motivations for us to do this project? Well, under the Christian worldview and our views on human values, we learn from the Bible that all people were made in the image of God, right? From Genesis 1:27, every single person has intrinsic value, and that means no person, no matter where they are, where they're from, deserves to be treated poorly or live in poor conditions that are non-dignifying. Furthermore, in general, Christians are so called to serve the poor. So what are we doing if we're not helping people who are in need, right? Um, Also, like as engineers who are lucky enough to go to college and gain these skills, These skills aren't ours. They're given to us by God to serve others, right? They're not made to glorify ourselves. So we want to use these skills to care for others and empower this community and share the love of Christ, right? It could save so many lives and bring people to Christ. So, yeah, we want them to have water access that enables them to have dignity education and further opportunity. Okay, so now let's get into the meat and bones of this project. So we were tasked with designing two different water towers to be proposed for this area. And as you already know, the tank capacity should be about 140,000 gallons. This reduces a high vertical load onto the truss that we're going to be designing below. So we want this truss to both be like stable, um, cost effective, and easily constructible. It's not supposed to be the fanciest, highest water tower because that's not something easy to maintain. It's more likely to experience stress under load. It's just supposed to do its job and do its job as well. So the tower can be up to 130 feet high. We certainly are not going to go that high due to the reasons I just explained. So the loads that a water tower usually has to withstand in a truss is just simply the weight from the water in the tank, and then furthermore the winds that blow on the tank. So we're going to be doing some simulations and hand calculations on the truss structure itself to see if it can handle the loads that it will be experiencing, and then we can select the materials and the truss design from there. Um, yes, we will make evaluation on both of our designs based on cost, stability, the simplicity, and the materials that we use to see which water tower we choose. And yeah,
Hi, my name is Frank Martinez. I'll be going over the next couple slides. So this is our general design specification slide. This requires that our tank has ASTM 836 steel with a half-inch thickness in a spherical shape. Our tower is a maximum height of 130 feet, and our max width is 45 feet. And our trusses obviously need to be able to support a vertical and a wind load. Alright, so our first design concept, which is design A, features a square base of 25 of 25 feet double layer truss. The ground connections, we have two opposite corners. One is a roller and the other corner is a pin. And this design, through our simulations and our hand calculations, was deemed to be able to support the wind forces in the horizontal as well as the vertical load forces. Okay, so for design B, we had a very similar choice to design A. However, this one features an X-shaped internal truss. The same layout has for the pin and roller connections to one in opposing corners, and then we ran into some issues with this one where it has a overall higher deflection as well as an uneven force distribution. And of course, it is constructed with ASTM 836 steel. Alright, so to discuss some of the results in our simulation for design A, we can see that TBC and TAD, those are our supports, our limbs that are taking on the vertical load. So usually TAD, TABC, you can see that they'll take on just about an even distribution of the vertical load. However, except for the wind on twice average wind and full capacity, you can see that actually TAD takes on significantly more pounds force than the TBC, likely due to the shifting of the structure with the wind. And then looking at some other limbs, TBA never shows any pounds force in that. TDC and TAC, those are horizontal verticals, so they only take on the force of the wind coming in. And then for our deflection, pretty negligible all throughout, with obviously the lowest values being at no wind, half capacity, and then going up from there as we increase our overall loads. Alright, taking a look at design B, the simulation results here. There's a lot of data here, but the important things to note are we take a look at limb F13, F24, F35, and F46. These are actually the vertical bars going through our structure. And you can see these actually take on the most force compared to all the other limbs in here. And then the only other limb difference would be F34. That's our vertical bar in the middle of our structure, which also takes on some force, not too much. And then the rest would be the rest of our X-shaped limbs. So it's interesting to note that looking at just about every single limb here, none of them take on too much of a significant amount of force. Especially F38, that one takes on 0. F47 takes on considerably more than the rest, so that's something to note there. And then we take a look at deflection. We have higher deflection overall on the structure compared to design A. Alright, so here we have the hand calculations versus simulation data. We have two different graphs to keep things concise. We have design A, design B. graphing the force versus the truss member. Um, this is simulation data for wind speed, average wind speed at full capacity. So if you look at design A, you can actually see that there's no difference between the hand calculation and the simulation data, which is great because that gives us a 0% error. On design B, if we look at the graph, you see slight differences in the hand calculations versus the simulation data. This still gives us a very low percent error of about 4.43% on average. Although there are some members that have a slightly higher percent error, such as member F47, which has a percent error of 11.5 on average. This could be due to any number of things, although most notably perhaps how SOLIDWORKS handles the geometry of the member or the calculations. Alright, here we have our truss load calculations. For design A and design B, they both use methods of joints. And design B is just a bit longer just because we have more joints.
So we ultimately decided to go with design A over design B, and there are a couple reasons for that. First off, in design A, it looked as if the forces were being evenly distributed throughout the truss rather than just one or two specific areas like design B was. This would prevent early failure or a total loss in the water tower truss structure. Also, when we did simulations in SolidWorks, design A had a lot lower deflection points, pretty much in every single condition that we had applied. And then lastly, design A also had identical numbers when we compared it to our hand calculations and calculations we did in MATLAB. This ultimately proving that design A was the best choice for the current job needed. Here is the product drawing that we had of design A. As you can see, it's that truss structure with pretty much just a square shape with that diagonal bar going across it just to give it a little bit more stability. This was the final design that we chose, and everything from that previous slide, all that information matches this truss structure that we had made. These are all the materials that are going to be needed to start breaking ground and get that water tower fully assembled beginning to end. So what we decided to do was use a ASTM A36 steel, and we did a little bit of research on the sizes that we needed to give it the most stability. And this is the amount that we have so far. We need about 12 25-foot steel tubes, 2 36-foot steel tubes for the diagonal portion of the truss. We need some steel plates, grade 8 structural steel bolts, welding supplies to put a good chunk of this together, paint to protect the outside of the water tower, concrete footings to just give it that stability on the ground so that it's not going anywhere, because that would obviously not be a good thing at all. And then some other miscellaneous hardware to factor in there just in case, we ran out of something or if something else popped up that we may need. And a grand total cost would roughly come out to be about 10,000 US dollars to get this water tower fully assembled beginning to end. Alright, now we move on to the assembly instructions for the water tower. Step 1, we obviously need to prepare the site. We need to make sure that the ground is stable, the soil stable, so that this water tower, when it's fully assembled and built, is not going to fall, or the ground is not going to cause any extensive damage to the water tower, causing it to fail. Second step, we need to start placing the concrete, getting the footings placed for the water tower so that the truss can be built. Step 3, after the concrete is built, we need to start assembling the truss onto that concrete to make sure that it is stable and make sure that it's attached in all the right places so that that water tower is as stable as possible. The fourth step is going to be the tank placement on top of the truss, thus completing the stability portion of the truss to make sure that it will actually hold it and get this placed properly so that the water doesn't cause any damage to it. And then after this is done, a leak/load test needs to be conducted, meaning that all the weak points in the water tower are identified, all the leaky points are identified and welded up, and any other issues that we have with this water tower are taken care of, so that when it's left in the hands of the citizens of this area, it's not going to ultimately fail on them and put them back into a distressive state that they were at. After this training and inspection, the people that have assembled this water tower know how it works, so they need to ultimately train a couple of the civilians in this area on like things that may be warranting review. So if there were damages, or if it was leaking, or if something broke on this water tower, these civilians would know what to do. If they needed to contact somebody, they could do it, or if they knew how to fix it, they could also fix it themselves. Lastly, it's once everybody's trained up on it, once this water tower is completely assembled, it will be left to the civilians of this area and will continue to serve them. To conclude everything that we have gone over in this presentation, the final design will serve about 20,000 people in Kotito, Uganda, on approximately a 2-week water supply. Design A was proven to be the most beneficial, and it was proved through both simulation and calculation. And then the final design will be constructed of that ASTM A36 steel due to its ability to be easily repaired and manufactured. Here's our reference slide regarding the sources that were used for this project, and ultimately I hope that you were able to enjoy this presentation, and let's get this water tower built.